they'll just, this is just a rough idea, right? It can be postponed as well, that I understand. Just a rough idea I wanted to ask. Anyways, in your batch, your syllabus is almost towards the end. I just wanted to know, because if once your pre-boards are just, the date is decided, no, so accordingly we can have the dates for the revision class. That's right. All right, class. So let me just quickly revise what we have done in the last class, and let's carry forward with dual nature of matter and radiation. So dual nature of radiation and matter here, this is basically deals with, this is from the unit modern physics. So we had started with the concept of free electrons. So in metals, the electrons in the outer shells of the atoms, they are loosely bound and they move about freely throughout the lattice of positive ions. And such loosely bound electrons, so they are known as free electrons. So until and unless a certain wavelength, a certain frequency of light is hit at this electron, then this electron actually becomes available for conduction. Free electrons, it does not mean that your electrons are roaming around and can conduct electricity in any way you wish. No, electrons, free electrons, both have the difference that electrons, you can, free electrons, you just specify for those electrons which can be made free if certain frequency or energy is just there on metal surface, right? So there is a certain minimum amount of energy that is required for an electron to just escape from the metal surface. This is known as work function. So this is the minimum amount of energy that is required. No. Not on the, it can be in atomic level as well, Sana. It can be in atomic level as well. Not only on the surface. Microscopically at atomic level also, it's just that loosely bound electrons have their certain definition, as in they can be free, they can perform the work of conduction. Like if light is hit and an electron has a threshold, or let's say the electron needs 10 to the power minus 8 hertz frequency, and somehow you strike a light of 10 to the power minus 8 hertz frequency of that respective electron. So that electron, if it is a free electron, it means it has a tendency to get free. It is loosely bound, so it has a tendency to be free. So it can get free on the surface as well, within the surface as well. That is all relative. Understood? Okay. So yes, so this certain amount of energy that is required by the electrons, this is known as work function. Work function is very important concept. This was the conversion which we had seen. Well, electron volt is 1.6 into 10 to the power minus 19 joules. Now, 4 types of emissions are possible. These 4 types, you even if you forget all the names, it is not very important to remember other names as well. But this last one, photoelectric emission, is important. See, class, in short, if thermal energy strikes on the electron, so thermionic emission of electron occurs, right? If cold cathode radiations are struck on it, then you say field energy emission occurs. If moving electrons collide among themselves and it results into emission of the next electron to which it has collided, that is known as secondary emission. If light rays are struck on the electron, so that is known as photoelectric emission. Photoelectric, light is making the electron free. So photoelectric effect is a part of your syllabus. That is important. Even if you forget the names of the rest of it, no big issue. Now see, so photoelectric effect is what? If a light is there which is having a certain suitable frequency. When I say the word certain suitable frequency, certain suitable wavelength, it basically means that that electron is having certain values. Like let's say in normal your system, let's say the passing marks are, let's say, 33% out of 100, right? So to pass, to go into the next standard, you require minimum of 33% marks, right? So if a student is getting 20%, then the student will be declared fail. The person will not be able to move into the next standard. But if the person even scores 34%, the person scores 90%, the person scores 85%, all these will be considered pass. Now, one is the higher score, one is a lower score. That is a different topic. So same thing is here as well. Every electron has its minimum cut-off value that has to be crossed for its emission, for it to move into the another stage, you can say, just for your remembrance, into, you can say, in conduction, wherever conduction is required. So if that minimum, even if 0.0 by 0.01% it is exceeding the threshold, then that will be considered. And regarding what value, let's say 5 hertz of frequency was required and the wave had, let's say, 90 hertz of frequency. So 90 is greater than 5. No. Now what will be the effect of higher frequency? That is a different topic. The way I had said, one who is getting 90% marks and the one who is getting 34% marks, both are though considered as pass. But there is a certain difference. One is getting a higher score, one is getting a lower score. That is a different topic. Same thing in here, whether it's 90 hertz or 5 hertz. If it has been crossed, then the electron is available. Now, effect of frequency, effect of intensity. To check all these phenomena, no, there were certain experiments made. Vacuum tube was connected, the whole apparatus, ammeter, voltmeter, rheostat, battery, key, everything was connected and the setup was set. This setup will not be asked to you in the examination to draw, but the conclusions of it is important. So the first conclusion, I think we had stopped at this point only. We didn't go further. We didn't do the effect of potential or frequency. I'll discuss it that right now. So first effect was, when you increase, this was done experimentally, class. Totally all these results were done experimentally. So do not worry about how it was done, how the formula is derived, how the derivation is done. Do not worry about it. Simply see, just understand, if we allow the radiations of a fixed frequency to fall on that plate, the plate that I had shown you, the vacuum tube, and the accelerating potential difference between the two electrodes is kept fixed. Potential difference is fixed. And you have allowed radiations of fixed frequency to fall on it. Then you will notice that the photoelectric current is found to increase linearly with the intensity of incident radiation, as I have drawn it in this figure, this graph basically. As you increase the value of intensity, photoelectric current increases by the same amount. Even if it is increasing by smaller amount, it is also increasing by smaller amount. So it increases linearly. So since the photoelectric current is directly proportional to number of photoelectrons emitted per second. So this implies what? That number of photoelectrons that are emitted, whatever is the number of photoelectrons. Yes, electrons that get emitted by photoelectric effect, those are known as photoelectrons. This I had, I think, told you also in the last class. So number of photoelectrons that are emitted, that is also proportional to intensity. So here we had stopped. This was a revision of what we have done. Any doubts still here? Please keep on clarifying in between. Now, second thing is potential. So see, class, do not note it down. I'll give you time to note down these effects: effect of frequency, effect of intensity, and effect of potential. All these three are important. So intensity, we have seen, increases linearly. Now see, the way I say, a certain frequency is required for which the and also class, if by chance my voice is cracking in between, my voice is breaking, please let me know, because I'm having internet issues today. So it can happen that my voice will not be as audible as it is. So please just interrupt me in between if my voice is not audible or the screen is not sharing. Right now, I hope I'm audible. Yes, class. Okay. So yes, so the way I say, a certain minimum amount of frequency or minimum amount of certain wavelength is required for the photoelectric emission to occur. Same way, there's a certain value of potential also that is required for photoelectric effect to occur. So that there is a negative potential for which the photoelectric current immediately becomes zero, right? Whenever a certain frequency of incident ray is struck on it. So that potential for which the current becomes zero, or you can see the minimum potential that is required for photoelectric emission to occur. This is known as stopping potential. Maximum or commonly used name is stopping potential only. But it can happen, you will find it as cutoff potential also. So if you find it as cutoff potential, do not get confused. Both are same. So it's like certain criteria is there. Certain wavelength has to be there. Certain frequency has to be there. So likewise, you have certain potential also that is required. That is known as stopping potential. Now, how will you draw the graph of stopping potential? So you don't need to apply your brain on how to draw it. You just have to remember it, because these are done experimentally by the scientists. You just have to remember, and you have to remember the conclusion. Like, this will be given to you. It can be asked, compare the order of intensities. So I3 is greater or I2 is greater, I1. Like this questions will be asked. Or simply plot the graph between photoelectric current and the stopping potential like this. So like this question will only come, as I'm saying, please focus on ray optics. At the complete entire optics rather, it is much more difficult. These modern physics 3 chapters and semiconductors, you will be able to manage it. Anyways, now see how the graph looks like. This is how the graph as I have already shown. If you keep the intensity, intensity is different over here, right? Intensity is here is different. Frequency here is fixed. Just remember one point, class. Here, no. Frequency is fixed. Intensity is variable, but frequency is fixed. Now see, gradually, what has happened? You increase the positive potential, right? You increase the positive potential gradually. So it is found what? C class, photoelectric current. This photoelectric current that you're obtaining on this y-axis. So photoelectric current, this increases with the increase in accelerating potential. Did you notice? When the potential increased, this is the y-axis that is having the value of potential energy. And this is the value of stopping potential on the negative x-axis. So if you're increasing value of stopping potential, value of photoelectric current is also increasing. See on the graph, this is in the second quadrant. So look at it in the second quadrant. This value, it is increasing, it is increasing, it is increasing. But see, it has increased till a stage is reached when the photoelectric current has become maximum. And it does not increase further with the increase in the accelerating potential now. This final step. Right, this is now not increased. Also, one more thing, class. This maximum value of the photoelectric current, this is known as saturation current. You want, you can note it down. This maximum value, this is known as, in the next graph, I have written it already. Saturation current. So for different, if you keep on increasing the intensity, the graph steepness will keep on increasing above, right? So you have to understand that the greatest intensity is the maximum, that is having the maximum value of photoelectric current. Because obviously intensity and photoelectric current are directly proportional to each other. So if here the intensity is maximum, here if the photoelectric current is maximum, intensity will automatically become greater. So this is what is the graph, how the graph looks like, what is the graph. But one relation you have to know between kinetic energy and stopping potential, because work function, kinetic energy, stopping potential, threshold frequency, threshold wavelength, all in your numerical part. You have numericals from here. Not very difficult numericals. Some standardized numericals are fixed. Those are there in your syllabus that we'll discuss also. So for that, you require relation between kinetic energy and the stopping potential. So C class. Electronic charge multiplied by the stopping potential. This is the electronic charge. Electronic charge is 1.6 into 10 to the power minus 19. And this is the stopping potential. Modern physics has a lot of theory portion. I did not get those notes. I'll get it by Wednesday or Thursday. So most probably I'll share it on the group directly, the notes for it. I have handwritten notes with me for the entire three, I think, till nuclei also. I just have to check it once. So I'll share that with you, the notes, handwritten notes. So that's why I'm writing very limited definitions. Otherwise, this has a lot of definition. Every term has a lot of definition in this. The whole analysis of the graph, which I had discussed just right now with you, that has to be written by all of you in the exam. Fine. All right. So yes, so kinetic energy maximum is EV naught. This is one relation to it. Fine. Are we clear till here? Effect of stopping potential. First was effect of intensity. We had seen directly. Stopping potential directly, but to a maximum value. Last one also let us discuss. That is effect of frequency. All right, this is the effect of frequency. Now, see, to study the effect of the frequency on photoelectric effect, intensity of the incident radiation at every frequency. It was adjusted in such a manner that saturation current became same. Intensity was adjusted in such a manner that for all the values of frequency, a single saturation current was obtained. You can even look at the graph. All three are pointing and are getting combined at a single value of the maximum saturation current. Fine. So here this just basically shows that as you are increasing the values, as the stopping potential has become more negative, frequency is increasing. Fine, that is showing you that frequency is increasing. So this implies what? This implies that greater the frequency of incident radiation, greater is the kinetic energy, and greater is the potential that is required to stop electrons. Understood? I'll write down the statement. See, this graph basically tells you the fact that, see, greater the frequency, that is of the incident radiation, greater is the kinetic energy maximum. Maximum value of kinetic energy is more because of the frequency of the electrons that are getting ejected. And because of this, you have the greater value of the stopping potential required to stop the electrons. This is what is the conclusion you can draw from the graph. All right, so till here, I think you should note it down. These are the three variables, you can say, or the factors which can come along with all rest of the quantities for photoelectric effect. And these three graphs, any of the graphs can be asked directly. So you just have to plot it as it is, that has been written on the screen, as it is, no difference. Because this I have taken from NCERT only. In NCERT only it is mentioned. All right, one graph you have that is important from numerical perspective that I'll tell you. First, you note down these points that I'll tell you. So till intensity, you all have written already. From here, note it down. And any doubts you have, please get it clarified. Class, one more thing, one definition I think I did not tell you, no, about the threshold frequency. We didn't write the definition anywhere. Stopping potentials and photoelectric effect, work function beta. Threshold frequencies definition is also important. Threshold frequency, same thing, the minimum value of the frequency that is required for photoelectric emission to occur. But that definition you all should have. Threshold frequency. So it's the minimum value of frequency, the minimum value of frequency. So of the incident radiation, obviously, of incident radiation below which or for which photoelectric emission occurs is called threshold frequency. See, frequency of the light is denoted by nu, symbol nu. Usually for threshold term, no, we add this not, so that this differentiates. All right, so that this differentiates with it. One more thing, maximum kinetic energy, no, if you see kinetic energy of photoelectron, that also increases linearly with the frequency of incident radiation, but it is independent of intensity, because this question I have seen a lot in the previous years. One thing, see, kinetic energy and frequency. If you plot a graph, if you plot a graph, it can come as a graphical question as well as it can come separately also. C class. If you see the graph between kinetic energy and the frequency, it will also be a straight line. But if you see the graph between kinetic energy and intensity, so this is independent. So it can come as theory part as well as it can be asked to you directly. Now see, if you are asked what are the laws of photoelectric emission, I'm not, as I've said, I'll give you the notes only, I'm not writing everything in detail. But if you are separately asked on the laws of photoelectric emission, so see, some things you have to keep in mind, like you have to first tell the definition. And in the first point of laws of emission, also laws of photoelectric emission, the first point is same thing only, that photoelectric emission is directly proportional to the intensity. This is the first point. Second point is regarding the threshold frequency, that a minimum value of threshold frequency is required for photoelectric emission to occur, the definition that we have written. Fine. And one more thing, same thing, the graph that I have shown, that kinetic energy is dependent on frequency directly, but it is independent. Kinetic energy is independent of frequency. Or I'll write it directly. Kinetic energy is, sorry, not frequency, intensity. So kinetic energy is independent of intensity. This is the third law. Intensity. Intensity is power per unit area per unit time. Intensity is power per unit area per unit time. Like if I say intensity is high, it means number of electrons that are getting ejected, they are also very high. Fine, this is what is meant by it. Number of electrons that are getting ejected is high. So that is what is meant by intensity. Intensity is same thing, like intensity of a light. Higher intensity, brighter light. Lower intensity, lesser light. Same intensity. The intensity is not different. Frequency, see, frequency is number of electrons that are getting emitted. Intensity is regarding power. Intensity is a term that is related to power. How much luminous a lamp can be. That you can say that is the intensity of the power regarding how much what it is holding, right? Frequency is number of electrons that are getting ejected. And one last law also you have. Yes. I remember. A photoelectric effect is instantaneous process. Photoelectric emission is instantaneous emission. So I think 10 to the power minus 7 or 10 to the power minus 9 seconds. Yes, 10 to the power minus 9 seconds is required for photoelectric emission and the whole complete process to end. So all these things we have studied separately, but if it comes to you, what are the laws of photoelectric effect that do mention it like this? All right, do mention it separately. Noted till here, then we'll do one very important topic from this lesson, that is Einstein photoelectric equation. All the numericals will come from there only. Planck constant and all these terms will come from there only. So write it down, then we'll let's start with the mathematical part of it. From here. All right, noted down. Sorry, one thing, Sana, I think you were asking. No, it's not power per unit area per unit time. That is power by area, just power by area. If I have to include time, that will become energy per unit area per unit time. So if it is power, then it will just be Class, this part is important, so please pay attention for a while. This part is the most important part from this lesson. Then if you have understood this part, then I think all the questions of this lesson will be solved. So you have Einstein's theory of photoelectric effect. Because in maximum numericals, no, you will be having this, because the very basic easy numericals are usually not asked. I hope you've written the above part. Now, C class. First thing, no, as I have discussed with you, that as the photoelectrons increase, the intensity will also increase and the frequency will also increase. So energy of photons, you can say, or the light rays, this is directly proportional to the frequency. So E is directly proportional to frequency. Here you get a constant term. Here you get a value of a constant term. This constant term, this is known as Planck's constant. That comes here. This is denoted by the symbol H. So E is equal to H nu. This is not the Einstein's theory. This is just the part before the Einstein's theory. Now, what is this H? Similar basic constant is there. That is known as Planck's constant. So value of Planck's constant, all of you should remember. All of you. This value is very, very important. So this is 6.63 into 10 to the power minus 34. This will become joule per second. All right, this value is here. So this is what? This is the energy of the incident light. Even you can modify this. See, frequency is equal to speed divided by wavelength, because we all know speed is frequency multiplied by wavelength. So from here you can use this formula as well, hc divided by lambda. It means values of frequency you can keep. So this becomes hc divided by lambda, where c is the speed of light. And class, you already know the value of h, speed of light, you already know. So try to multiply both the terms and keep it with you for the ease of your calculation, because you will see most of the times you'll be getting hc together. So it's better if you see whatever is, I think 19 point something it comes. I do not remember it right now. 19.89 into 10 to the power minus 26. Like this it comes if you multiply both of it. Yes, yes. I'll write it down. Okay, Salman. So this is 19.86 or 89. Just cross check. Please cross check this value. I remember this, but it can happen that it might be wrong. Joules meter. So in the numericals, no, if you are getting HC, directly solve this value. Fine. So, and this is the wavelength. So in terms of wavelength also you can write. So this is the number of photons per second. Now coming to the Einstein's equation, Einstein's theory. What did he say? See, I have told you the concept of work function also. That is also some amount of energy. Remember work function in the starting only of today's class, that this is the work function. This is some amount of energy. This is also amount of energy only that is needed by the electrons or by the metal surface to eject the electron for photoelectric emission to occur, right? So one energy is the energy of photon, one energy is the work function, one more energy we discussed in between, remember, kinetic energy, which was equal to half mv square or ev naught. This was also one energy. 19.89, no? Okay, Sana, then I think the value will be same, because I just recalled it. I didn't solve it right now. That's why I wanted someone to cross check. Thank you, Sana. Now see, a photon and an electron will interact with each other, and that will result into photoelectric emission. That is what was said by Einstein's theory, or it was mentioned in Einstein's theory. C class. Incident radiation is there. Incident radiation that is falling on a bound electron. This is a bound electron right now. This has to be made free because it has the tendency, if the suitable frequency, that is h nu, h into nu, that is the some amount of the energy that is required. And this is, let's say, the incident photon. This is the incident photon. And this amount of energy is required. When you give this amount of energy, it means the photoelectron has been ejected, right? This is what? This is now the photoelectron. Photoelectron that has been ejected. And also, since this electron is coming out, this is moving, certain kinetic energy will be there. And one energy will be the work function, right? Because this amount of energy was required. And the amount of energy that was involved in the motion, the kinetic energy. So see, free electrons are bound within the metal due to restraining forces on surface. Work function you are aware of, minimum energy that is required to liberate an electron from metal surface. Now, Einstein's equation said that total energy that is present in this entire process of photoelectric effect, the entire energy that is present, this is not only work function, this is kinetic energy as well. So it means, how will you say? The total energy of incident photon, the total energy of the incident photon means this ray, this entire that is being incident on the metal surface. This is your metal surface right now. Consider this as a metal surface right now. So this is the incident photon. So total energy that this incident photon is holding, it's not just the simply h nu. It has work function as well. See, and it has this maximum kinetic energy as well. Kinetic energy maximum. So it has kinetic energy maximum value plus the work function. This is what is Einstein's theory. Now see, you can write it. See, energy of incident photon. I right now have told you this is h nu. Kinetic energy is kinetic energy max plus work function. Now there are numerous ways to modify it and write it. I'll write it down so that in numericals it will be helpful for you. See, we can write this as complete half mv square as well. Half mv square plus work function. Also one more thing, class. See, class, the way E is equal to h nu, no? Here, E is equal to h nu. Yeah, E is equal to h nu. Same thing, work function is also a type of energy only. So that is equal to h nu naught. This is also there. This becomes what? Nu naught, phi naught is work function. H is Planck's constant. Nu naught is threshold frequency. How could I write this? How did I relate this? Same thing. See, energy, cutoff energy is equal to Planck's constant into cutoff frequency. Incident energy is equal to Planck's constant into incident frequency. Same thing. Cutoff energy is equal to Planck's constant into cutoff frequency. So same thing that I have written. Now you can modify it here in this equation as well. One equation is this that you can write, or you can even write half mv square is equal to phi naught minus h nu. Or you can write phi naught as h nu naught. No, this will become h nu minus phi naught. No. H nu minus phi naught. So this, because phi naught is going on the other side. So this becomes h nu minus phi naught. So this can be written as h nu minus h nu naught. Remember, just now I've told you, which can be written as H common nu minus nu. All these formula are applicable. Whichever manner you want to change. If you wish, if you think at certain place kinetic energy is not, or energy, all the energies are given in electron volt, you can even write EV naught is equal to H nu minus phi naught, because kinetic energy is equal to EV naught. Now you can modify and rate it in whichever manner you want. You can write EV naught is equal to H nu minus nu naught. Same thing, whatever modification, because basic things you are now aware of, and all the numericals will be from now. You are in a state, you are in a condition, you can solve numericals. Any manner you can modify. See class, the way E is equal to H nu, phi is equal to H nu naught. The way E is equal to HC by lambda, phi is equal to HC by lambda naught. That is the threshold wavelength. This is the threshold. All these formula you don't need to remember, class. This is just, I'm keep on substituting. Don't think these are 15 to 16 new formula. The one formula is this. Total energy is equal to maximum kinetic energy plus work function. Now, you know this work function. Work function can be written as H nu naught. You know work function can be left as work function only. You know work function can be written as Hc by lambda naught. So you can substitute. Kinetic energy, I have told you maximum kinetic energy can be written as simply half mv square also. Kinetic energy can be written as EV naught also. So substitute any combination, make any combination. You know E is equal to H nu. You also know is equal to Hc by lambda. So modifications, all you just have to remember all these steps. Now any combination, you can make it by yourself. Any combination. Whatever is demanded by the question, write accordingly. Now you are completely in a state to answer all the numericals. Everything now you know that is required in this lesson to solve a numerical. If you want to substitute Hc by lambda, suppose let's say kinetic energy, a half mv squared is equal to total energy, that is Hc by lambda, minus work function. So write it as Hc by lambda naught if you think this is required. Take Hc common, write 1 by lambda minus 1 by lambda naught. Do you see? Is it any new thing? Just remember these basic things. See, I think this page is very important, this slide. This formula and the variations of all of these here, here, here. And then just combine it and then just simply write it and combine. Noted till here. Any doubts you have, let me know. Clarify it right here only. We'll solve numericals based on this. And do mark this as the most important part of this lesson. Whenever you are revising, at least have a look at this part once. See class, here frequency is asked, energy is given. So E is equal to h nu. Right. Now see, Planck's constant is in joule, 6.63 into 10 to the power minus 34. So electron volts conversion, I have already told you how to convert it. So 66.3 electron volt. This will be 66.3 into 10 to the power minus 19 into 1.6. This much joules. Now frequency will be energy by Planck's constant. Energy is 66.3 into 1.6 into 10 to the power minus 19. Planck's constant is 6.63 into 10 to the power minus 34. So what will be the answer? 1.6, 10, 6, 16. So this will be 1.6 into 10 to the power 16 hertz. Just correct me if I'm like this. This is the very basic question. Let's do some more questions. Write it down. Please class, try to submit today's assignment. Whatever assignment you will get on photoelectric effect, whenever you will get. I'll share the questions today. Whenever you will get the assignments, do submit it. Because this is just the main part of it. And good questions I'll send you in the assignment. So please submit this assignment. Assignment due date. That I have to check because this assignment is not created. Today I'll send the questions, so that I do not know, sir. I think how much days do you get for an assignment? 1 week. In the next class, I'll let you know regarding this due date of assignment. Okay, class C. Frequency is given, monochromatic light of frequency 6 into 10 to the power 14 hertz. 6 into 10 to the power 14 hertz. This is produced by a laser. Power is given here. 2 into 10 to the power minus 3 watt. First part says what is the energy of each photon in light. See class, number of photons which are emitted per second. This is equal to power, right? Power by energy. This is one formula that is required. Otherwise, see, firstly, let us calculate in, now let us come back to the question. First part says what is the energy of each photon. So frequency is given, energy you can easily calculate. E is equal to h nu, frequency, no, energy we have to find out, no. So energy will be equal to Planck's constant into frequency. So that will be 3.98 into 34, 14. So 19 minus 19, 10 to the power minus 19 joules. This is the energy. Now, second part, number of photons are asked. So that will be power by energy. So power is how much given? 2 into 10 to the power minus 3. By energy was? Yes, 3.98 into 10 to the power minus 9. So if you solve this, what will you get? 2 by 3.9. So 200 by 398. Almost 400, you can take 2 by 400, right? So half or 0.5 you can take. So that becomes 5 into 10 to the power 15 photons per second. First tell me, is this question clear? The concept of power. Memuna, clear to you? Khalid, Salman, you there? Understood?
Yes, ma'am, understood. Yeah.
Okay, good. So note it down. If anyone is not able to understand, let me know. Sneha, I hope you're able to understand. In the last class, you were not there, but I hope this part is not very much related to the last part, then the revision has been done. Okay. Class, one question is there. Cesium metal. Work function of cesium is given as 1.8 electron volt. Light of 5,000 angstrom is incident on it. It means you have the wavelength, you have the work function. Fine, two things you have: wavelength of the light and work function. Now, threshold frequency and threshold function is asked in the first part. See, I have told you, using work function, you can find out threshold frequency and threshold wavelength. Work function is what? H nu naught, that is threshold frequency. Also, work function is hc by lambda naught. Lambda naught is threshold wavelength. And this was already given to you in the question as 1.8 electron volts, 1.8 eV. So let us convert it. Phi naught, this work function, it will be written as 1.8 into 1.6 into 10 to the power minus 19 joules. So phi naught for the threshold frequency, we'll have work function getting divided by Planck's constant. So 1.8 into 1.6 into 10 to the power minus 19 by 6.63 into 10 to the power minus 34. Whatever answer you'll get in hertz. This will be something 4, something it will come. Just check it once. And same thing for the threshold wavelength as well. Lambda naught will be equal to what? Hc by phi naught. So 6.63 into 10 to the power minus 34 into 3 into 10 to the power 8 meter per second. And this work function is how much? 1.8 into 1.6 into 10 to the power minus 19. This much of meters will be the wavelength. This is fine by all of you. See, work function's formula is this. Work function's formula is this as well. Nu naught is unknown. Phi naught is given. Phi naught is given. H you know, C you know. Lambda naught is unknown. So like this, you have to calculate if work function is given. Second part says maximum kinetic energy of the electrons. So kinetic energy is formula. Einstein's theory, whatever we have studied right now. Kinetic energy was this only, no? Hc by lambda, that is the total energy, minus whatever is the work function. See, wavelength is given, lambda of the light is given. No, this is lambda not which we had calculated. This is different. Lambda is also given, 5,000 angstrom. That becomes 5 into 10 to the power minus 7. Right, 5 into 10 to the power minus 7 meters. So lambda is given, phi naught is also given. So kinetic energy will be what? It will be 6.63 into 10 to the power minus 34 joule second into 3 into 10 to the power 8 meter per second by 5 into 10 to the power minus 7. This entire term will get subtracted from 1.8 into 1.6 into 10 to the power minus 19. This much of joules will be the answer for kinetic energy. Clear? I think third and fourth part are also there. Third part says what? Maximum velocity of emitted electron. See, once you have the value of kinetic energy, I think kinetic energy will, just check it once. This is the value that I remember, but it can be wrong. It was around 10 to the power minus 19. Means 1 point something was there. 0.89, like this it was there, into 10 to the power minus 19. This I remember that was there. This much joules. So just check it. This will be around 10 to the power minus 19. Let's assume it is 10 to the power minus 19 only. Forget this. I don't know whether this is correct or incorrect. See, in the third part, this is asking kinetic velocity maximum. So this is half mv max square only. So velocity maximum will be what? 2 times kinetic energy maximum divided by mass under root. So kinetic energy maximum value will be this. And yes, mass of what? Mass of cesium is not given, no? Okay, mass of emitted electrons, now we are calculating. So mass of electrons we'll keep. See, mass of electron, this is 9 into 10 to the power minus 31. We are calculating velocity of electron, no? So mass of electron is this, kinetic energy maximum from this part, mass here. Like this, you'll calculate V max. And the last part says what? If the intensity of light be doubled, then what will be the maximum kinetic energy of emitted electron? This part all of you answer right now. If intensity is doubled, what will be the maximum kinetic energy? Twice, thrice, it will also be doubled, 4 times, what? What do you say? Salman, what do you say? If intensity is doubled, yes, Sana. So only Sana has answered. Other than Sana. Salman, I was asking you. Okay, Salman. Yes, Neha. Intensity doubled. Will kinetic energy be doubled? It will be 4 times. It will be thrice. What? Sneha. Yes, Sneha. Memuna. Answer from you, Memuna. Kinetic energy is doubled. Intensity is doubled. Then what will happen to kinetic energy? Turn your pages. You must have written all of you somewhere. There was a relation between kinetic energy and intensity. Check it from there. Only Sana remembers. Apart from Sana, nobody has answered. Khalid. Intensity, if intensity of the light is doubled, so what will happen to kinetic energy? Will it be doubled, tripled? What will happen to kinetic energy? Yes, Khalid. At least make an effort to turn your pages what you have written in the theory part. No idea, Memona and Sneha. Okay, Khalid, Salman, I understand your network issue. What about Memona and Sneha? Both of you. Okay. At least Memona has tried and attempted to answer. See, both of you and others also. Didn't we make a graph between kinetic energy and intensity? For frequency also we had drawn. Are you people not paying attention in the class? Otherwise, I'll ask you all to open up your videos while the class is going. Didn't we plot these two graphs? That's why I was saying, even if you don't remember, turn your pages and see if you have written the notes. It means you people are not making the notes then. See, kinetic energy is directly proportional to frequency, but kinetic energy is independent of frequency. This graph also I made, and I told you this will be used in the numericals. It will be used in conceptual questions. Especially, I asked you all to note it. Like this only questions will come. This question, this you are writing, this question that we have discussed previously, that was also a question from your NCRT only. And this question is from previous year only. If intensity of light is doubled, there will be no effect on kinetic energy. So fourth part means it will remain unchanged. For the fourth part, kinetic energy remains unchanged. Please pay attention in the class. If you are having any doubts, clarify it. Otherwise, it will become very difficult. Note this down. Wherever you still you're not able to understand, let me know. And for students who are having network issues like Khalid, Salman has left only. So all those who are having, you got kinetic energy is so 10 to the power 19, no? 1.098. Okay, good, Sana. Correct answer. And I was saying for students like Khalid and Salman, Salman is not there, but Khalid, whoever is having network issue, if any part has been missed by you while you were disconnected, no, then let me know that part. If it's a bigger portion, that obviously you can see from the recording later on. But it's a very small doubt that you're not able to understand because of network issues, so just ask me, I'll repeat it once. See, there's a graph that comes. This is the last topic for today, and that will almost finish off with this lesson. So in the next class, we'll start with a new lesson. Please prepare with this chapter. Next week, you will have a test of this. Not this Wednesday, next Wednesday or next Monday. But please be prepared with this. This is a very short lesson. Only this part will come, what we have studied. So there's a graph showing variation. This graph comes separately, showing variation of stopping potential and frequency. See, if you plot the graph now between stopping potential and frequency, let me show you. So see, this we have studied. If this is stopping potential on the y-axis, this is stopping potential on the y-axis, and this is frequency of incident radiation on the x-axis. So this I have told you, both of them are linear to each other. So graph is a straight line. Okay. Notes of which lessons? Dual nature only or wave optics as well? Khalid, just tell me the name of the lessons. I'll share you. I hope I'm audible to you, Khalid. If you're able to hear me, no, because if your internet is not working, just let me tell me the name of the lesson. I'll share it. Only dual nature. Okay, Khalid. I'll share the link. So see, this is a straight line. But see, if you extend this, if you produce this, this will reach a location. This is basically work function divided by the electronic charge. Now, negative also you can add because this is below the positive axis, that is, this is on the negative y-axis. Now see class, meaning of all these terms, what we have studied. See, electron, that is total kinetic energy, can be written as total energy minus the work function. If you divide it by E, this becomes h nu by E minus work function by E, right? This is it. Now compare it with this equation. See, take this separately and compare it with the linear equation. Y is equal to mx plus c. Do you notice the slope is this? Y-intercept is this. That's why in the graph, I have written minus phi naught by E here, this as the y-intercept. Understood? Because of the calculation. And if you take the slope, if you want to take the slope is taken like this, theta, let's say. So if you want to take the slope, you take tan theta, which is the slope. This will be equal to h by E. This is an important graph that comes. Okay, note this down. I'll stop after this. This completes your photoelectric effect. 5 to 10 minutes will be taken on de Broglie, but that I'll complete in the next class only. Then I'll just start with the next lesson, that is your atoms. Atoms is also a smaller chapter. Note it down, text me done when you have completed. All those who have completed, you all can leave. Class is over. Thank you so much. We'll continue this on Wednesday then.